All right, so we're going to do some examples of these new subrings generated by an element. This is one way they're sometimes talked about. All right, so we did one already, so I just want to jot that down. We decided that z adjoin pi, this was the set of all s0 and pi, s2 pi squared, so these are all real numbers. And we were allowed to use any coefficients, sorry, SI, that were integers, and then powers of pi up to whatever power we wanted. So this contains things like 3 minus 2 pi plus 18 pi to the fifth. Okay, so it contains things of that form. So polynomial expressions with pi. All right, let's do another example to see the kinds of things that can happen here. So let's stick with integers this time as our subring again, but let's use the number 1/2 as an element of our larger ring that we're going to add in. So here, if I just use my definition, I can write it out just like above, but then we can kind of clean it up a little bit. So this time I have S0, S1 times 1/2, S2 times 1/2 squared, all the way up to some Sn times 1/2 to the nth. And again, those Si's are integers. So let's think about what this contains. So it contains things like, let's see, so 3 plus 7 times 1/2 plus 8 times 1/2 cubed plus dot dot dot, and I just have to end somewhere. So actually, let me just not do the dot dot dot. Let's just end with that 1/2 cubed. So that's a number that's in this set. But we usually don't write that number like this. We usually would get a common denominator. So let's say that's a 3 and a 7/2 and an 8/8. So really what we end up with is 4 plus 7/2, or 8 plus 7/2, 8 plus 7/2, or 15/2. We would write it something like that. We might even want to write it as 7.5 or 7.5. So let's think about all the things that would be in here. So let me try another example of something that's in that set. Something like -1 plus 3 times 1/2 squared plus 5 times 1/2 to the fourth. So if I wanted to rewrite this one, so I've got my -1, that's fine. 3 times 1/2 squared is really a 3/4. 5 times 1/2 to the fourth, 5/16. So again, if I wanted to simplify this, I would really just put it all over 16. I would get my common denominator and add all of that up, and I'm not going to worry about what it actually comes out to be. There's going to be some integer on the top and a 16 in the denominator. So if I want to be able to generalize this, what all the things in here, what's happening is I can have whatever integer I want on the top, let's call it s, and then the denominator, because we're only using powers of 1/2, the denominator is always going to be a power of 2. So s is an integer, and n is some integer greater than or equal to 0. This is all numbers of the form any integer you want over 2 to the n. And you may see this example again in some homework problems, or you may have seen it already. All right, let's try some more. So the point of this example and the ones going forward is we know how to define this as these polynomial expressions, but sometimes we can clean that up and write it in a better way. So let's see another one like that. So let's do q adjoin square root of 2. Okay, so first stab at it is to say, right, this is polynomial expressions with root powers of root 2 and coefficients that are rational numbers. So things like this. All of my SI's this time are rational numbers, but I have these polynomial expressions, so I can use any rational number I want as coefficient and powers of root 2. So if we think about what happens here, for example, I could have 1 plus 7 root 2 plus 3 root 2 squared plus 4 root 2 cubed. There's a number that's in this set, but again, this isn't the best way to write down this number, right? I can rewrite this as 1 plus 7 root 2 plus 3 times root 2 squared is just 2. 4 times root 2 cubed, that's just 2 times root 2. And so I can clean this up even further and say, well, then really I have 1 plus 6, so 7, and 7 root 2's and another 8 root 2's means I have 15 root 2's. And if you think through any polynomial expression like this, with root 2, I can always reduce like this. Any power of root 2 I can bring back to either just 2 or some power of 2, or I might need a single root 2 in there. All right, so q adjoin root 2. I can write it as all these polynomial expressions, allow any power you want to, but really when it comes down to it, I can simplify and allow only expressions of the form a plus b root 2. That's really all I need here. All right, let's try another one. What if we do q adjoin 2 to the 1/3, so a cubed root of 2 this time instead of a square root of 2. So now again, my definition says I need all these polynomial expressions using powers of 2 to the 1/3. So let's see if we can again clean that up. So first, and maybe I should write this as 2 to the 1/3 squared. Okay, I have all these powers of 2 to the 1/3, and the s's again, si's are all in q. Okay, so now let's think about how can we simplify these numbers. So as a little example, what if I had 1 plus 2 times 2 to the 1/3 plus 7 times 2 to the 1/3 squared plus 2 times 2 to the 1/3 to the 4th power. How would I simplify that expression? So I have 1. I have 2 times 2 to the 1/3. I can't really do much to that. 7 times 2 to the 1/3 squared. I can rewrite that as 7 times 2 to the 2/3. And 2 times 2 to the 1/3 to the 4th. So that's a 2. This is now a 2 to the 4/3, okay, which I can simplify. So here we are, 2 times 2 to the 1/3, 7 times 2 to the 2/3, that's fine. Oops, and this was a plus. 2 to the 4/3 I can write as 2 to the 1st times 2 to the 1/3, right? And so total I have 1, I have 2 to the 2 to the 1/3, I have 7 times 2 to the 2/3, and I have 4 times 2 to the 1/3. So combining like terms one more time, it looks like I have 1, 2 to the 1/3, I have 2 of them, and another 4 of them. So I have 6, 2 to the 1/3, and I have 7, 2 to the 2/3. And that's the cleanest way to write this. So again, if you think through any longer expression like this, what it comes down to is that this particular set, q adjoin 2 to the 1/3, you can reduce any expression in here to an S0, an S1 times 2 to the 1/3, and an S2 times 2 to the 2/3. Everything else will be able to reduce down into just powers of just expressions of the form S0, S1, 2 to the 1/3, S2, 2 to the 2/3. So you'll try some more examples of this through some quiz questions, and then we will keep working with these things for many weeks to come.